So the last time we created a data structure for a graph and we created a breadth first search solution or algorithm or breadth first search find function that would look for a certain value in the graph starting from a source node and return that node if it was found or not. It would be a bit more useful perhaps if we could not just return whether we found something or not, or it would be nice for us to return the actual path between the two nodes using breadth first search algorithm. All right. So question might be, how could we possibly do that? Right. And here's one approach. So the approach goes as follows. Let's say we are starting from the root node, okay, and we're looking for a path to, let's say, to this node. All right. So let me mark. So this would be our destination. This is our source. This is some sort of graph. It's not necessarily a tree, but it's drawn, painted like a tree because that's how we walk through that graph. And if you recall, we could have edges actually even between those nodes so that it's not a pure tree. All right, so we start from the source, and what we do is we check out all the children of the source, and we check whether those children are the one that are our destination. If they are not, then here's the tricky part. We could actually save for each of these children, we could save who the parent is for these children. All right, and then we move on. We move on to all the rest of the nodes at the next level using the breadth first search. And as we're going there, we could also save who the parents of these nodes are. All right. So this way we are kind of building the overlaying tree that will define the path from every node to this source node. Okay. And as we're moving forward, we're looking for the nodes, and we have found finally our destination node. Then what we do, once again, we define the path back to its parent. And as we have found the destination, we can follow that path all the way to the source. Right? So in order to keep that path, we're going to have another data structure. And I'm going to call that data structure parents. Okay? And the type of this data structure is going to be a map, and it's going to be a mutable map so that we can change the values for these guys. And in fact, we may even get away without an immutable map in this case, because every time we're going to add a parent, that parent is not going to change for this particular algorithm. Right? So once we have found the destination, we just need to follow using that map to the parents, and that's how we can create the path. We could save that path in a list, and that list could be what we are returning. All right? So that's the blueprint, so to say, for the algorithm today to create pathfinding algorithm that's using breadth first search. All right. So let's go and look into the code. So in the code, we already have the breadth first search algorithm, breadth first search function, which I am going to reuse because it is tested, it works fine, and it implements the breadth first search. But I'm going to modify it to suit our purposes for pathfinding. Okay, so I'm going to make a copy of it. I'm going to call it BFS path. The parameters are the same, the source and the destination. But however, the defined type is going to be a list. We are going to return a path. All right. Now, what we have in this particular code so far, we start with the source node. We are enqueuing that source node in our toVisit queue with the nodes that need to be visited, or vertices. Often I call vertex a node. Sorry, that's just a habit, but they mean the same thing in this context today, right? And then we just walk through all the nodes that we need to visit from the queue until the queue is empty. Okay? So we take out the node from the queue. We check whether it's a destination. If it is the destination, we are going to have to build the path and return it. And return it. So when I have a somewhat more difficult task to program, often I use comments to kind of define the smaller tasks that I need to solve to keep track of them, and then I can either come back later and implement them, or it makes the code more readable as well, perhaps, right? So this is going to return the path, okay? Path. In order to return that path, we actually need to define it, okay? So therefore, we are going to have a value, and this value is going to be, let me call it a variable, path, and this is going to be of type list. All right, and we could actually assign it an empty list. But we need to be specific. What kind of list is it going to be? It's going to be a list of vertices. Okay, so that's going to be our path. And initially we create an empty list there. Now let's say there is no path, just like we return none in the search case. We could just return the same path, which initially is assigned an empty list object. So returning an empty list will mean that there is no path, right? Okay, so what do we need to do? We need to build the path whenever we encounter the final destination node, right? But before that, we need to actually keep track of the parents as we are descending through this breadth first search. So we need to create another data member. We need to create a map. Okay, so let me do that. And I promise that it's going to be called a map. Parents, and the type of it is going to be mutable map. Okay, and I even said that we may get away without changing the values of the map because we are not using weighted graph. If we were to use weighted graph, it might be that the parents may change to a better parent with a shorter path. But that we will talk about when we talk about the Dijkstra's algorithm. Okay, not at the moment yet. So it is a mutable map, not the match, map. And it's not mutable, but it's mutable map. All right. So the next task is to actually keep track of parents of the nodes as we are descending through the graph. Okay, where would be a good place to do that? So I think a good place for it to be whenever we go through all the edges of the graph, if we have not visited that particular vertex that this particular edge leads to, then we need to register it. So let's call it parents. Let's add a new node, and that particular node is going to be for the vertex V. The parent is going to be V0, right? Because we are looking up for the edges that are coming out from V0, and V is the actual node that one of those edges is leading to. So that's how we keep track of the parents. So that was a small addition to the depth-first search algorithm. In some places, it's not called parents. In some places, in some literature, they call it a memory to help us to keep track of, the parents of the nodes. There might be another way to implement it, starting actually from the destination and building up the path to the source. But this is how we are doing it today, right? Now that we have these parents, we should be able to recreate that path whenever we find the destination, okay? How are we going to do that? All right, so there's just one little problem with this. And the problem is that we have not included the actual, whenever we find the source, we have not included that one in the path. And that's why I'm gonna do it one more time here for the last node, okay? And perhaps there's a better way to order these things to make it nicer. So there's another comment in order. The way I have presented it here is we are going and rebuilding this path. But there might be some other data structures that are helping us out already. For example, later in Dijkstra's algorithm, we may use a data structure that's called a priority queue. But right here, we're just keeping it simple. All right, so since we have it like this, maybe we are ready to actually test it, right? So we are returning the path. And that path is going to be printed, except right now we don't want to run the BFS find. We are done with that part, but we want to run the BFS path algorithm. All right, let's see if we can. All right, and we do have an error. Okay, so what is the error here? And it's once again, it's one of those typo errors. So this arrow thingy should be actually pointing the other direction, right? Because we are creating an item for the map pointing from vertex, which is the parent, to its child, or rather from the child to its parent in this parents map, okay? And that's why there was the compilation error, I believe. Let's see, let's try it again. Okay, so we have a new problem here. And the problem here is actually to the point. The map requires two parameters. It requires the type for the key and also the type for the value. In our case, we are pointing from one vertex to another vertex, so therefore the types are going to be V. So this is fine. Should be now, right? That's programming. We write the code and we fix the mistakes and then we test them. So now let's see. We did try to find path from Riga to LA, and this is the result. The result is a list from Riga, DC, and LA. So that looks pretty good. Let's try something further. Let's try to VC, to Vancouver. So if you remember, we had this map from Riga, New York, DC, LA, and Vancouver. All right. Let's try it. And this should create a longer path, and yes, it does. Riga, DC, LA, Vancouver. All right, so we have created an algorithm, and we have programmed it for the graph class that finds a path. All right, and this is a fine algorithm that will work just fine unless you have your edges with weights attached to them. For that kind of case, we're probably going to need to use a different algorithm, which is called Dijkstra's algorithm. We also need to think about how to actually encode the weights for those edges in our graph, because right now there is no space for it. So that's going to be our next discussion, I believe. Thank you for